hope there is no background noise or airflow or something. There's nothing, right? Voice is clear and what audible, it's loud. Okay, so today's session on week 9. This is the first session on week 9, and this is an open session, open activity, whatever you will say. This session we will discuss like the concept, if you have doubt that, or activity, practice regarding that. Those we will discuss those, and along with the concept which in this week 9 I have covered. In week 9, the multivariable function now comes here. This is which is one kind of a function which contains more than one variable, and after introducing in the first lecture about the multivariable function, in the second lecture you will see partial derivative. You have seen partial derivative is one kind of like you have studied now. The calculus part is in math 1. Hope you all of you gone through the calculus portion. Without that, it will be difficult to understand this week 9. And today, whatever we will discuss also will be difficult to understand. I will try to be like that, so like so that you can understand more and more how much I can do. Am I audible? Swapnil, Shivam, Sekhajat, Satyam.
Yes, sir. Yes, sir.
Yes, sir.
And in the week 3, you will see about the limit of function. This is the limit of function for multivariable function. And head part is partial directional derivatives, continue, and directional derivative in terms of gradient. This thing is covered in this lecture, in this week. So let me start. Let me share my screen first. This is on week 9. So if you have doubt, you can ask. Then we will continue with that. Like once you will ask something like concept itself, we will continue with that. No one have doubt. I use Bhavna.
Yes, sir.
Sir,
Sir,
am I
actually,
audible?
Yeah, both are. Yeah, Bhavna.
Okay. Sir, I don't have doubt, but then I just want to understand if we have to prepare for quiz 2, is it okay if we go through all the practice assignment and graded assignment from week 1 to 8 and the mock quiz that we attended? Is that okay to prepare, or is there anything else also we need to just revise on for the quiz 2?
So I can say, that's the thing. Like practice or revising that thing is fine. Please attend mock, and please at least for those topics which is covered in mock is, already used to be a very simple kind of quiz. So at least you have to be very clear those topics which is covered in the mock. Maybe you can
Okay.
there's a like a question pattern, maybe somewhat can see. Please compare with the mock also. Please.
Yeah, I'm asking in addition to mock, is it sufficient enough if we go through all these, sir?
It will be enough if you go
Okay.
through activity and uh, this mock practice that
Mhm.
so let me start with the maybe anyone
Sir,
else
how
have
many questions are coming in quiz?
probably 10 question will be in each question maybe some part will be like in this mock you can see uh, like
Yes, sir.
there will be some part in one based question there will be abc kind of abc some part of the question like that the pattern also you can see that a question number how much the question number in mock also we will see in the similar as in page.
Okay, sir.
Let me start with the if you have a doubt you can ask otherwise I will start from the lecture itself like what is covered. In the first lecture, sir have talked about the function types of function like linear function, polynomial function, rational function, trigonometric function. These are all about the just introducing the basic thing because of now uh, math calculus person went in the math one. So previous like in term two, term three have calculus person was in math this math two, but now it is in math one. Just recalling those things, what is function, and in that itself you have seen what is linear, polynomial. So that this is just a recall. The main thing is about the multivariable. So once you have a function, like if you have gone through calculus portion, so if you've gone through in calculus portion, the function would be like this. You have seen maybe the domain portion is mainly concerned with this domain. This domain is maybe real number or maybe a subset of real number. This is in the first in calculus portion you have seen. But now in this from week 9, 10 and 11, you will see function. The domain will be R2 or R3 and codomain maybe it can be R2 or R3. It doesn't matter once you learn with this kind of function whose domain is R2 and codomain is real line or only just R. Then if the function is from R2 to R3 will be or any from anywhere or maybe this one. Let me not only two, maybe let's make it M. And so from Rm to R, if you learn with this kind of function, so it will be very easy to learn Rm to codomain will be whatever. So I will tell you how is the mean what is the mean of it, why it's make easy once you understand this kind of function. So in math 1 you gone through this kind of function, but in maths 2 it will be like rm2 some real line. This is, let me clear with that or let me give an example, then it will be more clear to you. So like for this kind of function it will be, let's say fx is equal to x square plus 1. Here you can see only one variable, but this kind of function is called you will see in uh, like this f of x is f of x y is equal to x y plus y square something. Like it contains two variables x and y. So that's mean here r, if let's assume with the let's stick with the only two variable, then we can easily extend to rm any finite number till any finite variable. So r2 to r, so this function would be like this xy plus y square. So it means this r cross r as you gone through the rm r2 r3 in vector space. So this is somewhat like you whatever you studied in the vector space, the static vector space r2 over r was very easy. So in this portion, the same thing, only this kind of thing, like only in this vector space you will study. So there is no mean to relate the vector space, but I am just saying what it means by the R2, R3. So it's make easier once you study about the R2 over R, like means generally saying to be R2 vector space or R3 vector space. So in this week 9, 10, and 11, we will see the vector space. You will work on the vector space over only just R2, R3, Rn kind of. So it makes easy to understand all those things. Are working like a or doing the all calculation very easy as a coordinate wise. That's me. And it will be a vector space as usual in R2, R2, R3 means coordinate wise addition and scalar multiplication used to do. So that's make easy to understand this vector space, and the same thing is here, just doing all things on the coordinate wise. So such kind of function is called multivariate function because it contains two variable. You can think the x value can be taken from this R and y values will be taken from this R, or maybe vice versa, or maybe this is for y, this is for x, whatever you will say, it will depend on that. So this is called multivariable. It contains two variable. It may be like this also. It this contains three variable, the zx, or maybe if I am writing like this only, x y z, x y plus y square. Still, this is a, we'll say, multi. This function contain three variable. Yeah, it is like a hiding z, 0 times z. So no need to be worry with this. This in three variable. This function is in three variable. If we denote it, it will be like R3 to R. So this is all about the saying to be a multivariate function. There are two types of function. If the codomain is just real number, this is called scalar valued function. It should be noted. It's like it is a very important, like whatever we study usually on this function we will study, that is means to say scalar, or sorry, scalar valued function. Scalar means whatever you will give, it will give a real number, only whatever you will get in R. But if your function like this, R3 to R2, so it means whatever you will get output, it will be in coordinate wise. Let me give an example. It is a function like this, xy plus z and z only. So this is one function. This is called vector valued. This kind of function called vector valued function. Am I audible?
Yeah, sir.
Yes.
Yes, sir. You are audible,
Yes,
sir.
sir. Yeah.
Okay. So this is called a vector valued function. As you can see, the codomain is contained, like codomain is will be a coordinate wise. So you can see this is first coordinate, this is second coordinate. So this kind of function called vector value. So this is all about in the first lecture. So knowing to be what is scalar valued function. So please be clear with that. Your function will be like this. Just 1 minute.
So scalar value means it is input is R1 and output is R2.
No. Input is maybe R2, R3, R3, but output is only
R1 or R. Okay. Output is R. Okay. And so vector valued means it output is R2 or R3.
Vector values, output is maybe R2, R3, or whatever.
Okay.
How much you want to be make your function. So it's depend on who is giving what kind of function. To knowing to be what is vector valued, what is scalar valued function.
So this week 9 will not come in the quiz 2 now.
No, only the syllabus is
After the quiz, it is end term 4.
Yeah.
Okay.
So this is all about in the first
So,
lecture. I hope it is clear what is
So your voice
scalar
is breaking, sir.
hmm. Okay, just 1 minute. Let me check. Is it now clear, Rohit?
Yes, sir. Yes, sir.
Is it now
Yeah,
clear? And
Yeah,
Yes, sir.
yeah, it is clear.
yeah. Can you repeat vector value function once again? Scalar value you mentioned it is Rn to R1, n being more than, 2 or more. But what is vector value function once again, please?
vector values is it will be look like, let's say I'm just making an example, R2 to R3 to R2. So this is input and this is output. So what it mean by output? It means whatever value you will get, it will be in two coordinates.
So
Like
again,
this.
sir, your
Like,
voice is break
for example,
for few
the
seconds.
input says R3. So that yeah, my showing answer my internet connection is unstable. Still, my site is somewhat raining day.
Okay. I
Like,
think that's why the internet is. Yeah. Okay. Yeah.
so please stop me once you didn't get what I said, or my voice is lacking, or you are not getting what I'm saying. So please stop me and
Sir, your voice was breaking, so I was not able to hear what you just said. You were explaining vector valued function, but I wasn't able to hear it.
okay. So is it now clear to you? Is it audible to you also?
Yeah, sir, now
Yes,
clear.
yes, sir. Now it is audible.
Now it is audible.
Previously, okay. Previously, it okay. So let me repeat again.
Okay, sir.
So what I'm saying, a scalar value, hope it is clear, very it is not obvious, it is very clear to it. The scalar value function is look like this. Input contains, this is says your r cross r. It means, this means that you are in giving the values from 3r. So that means it contains maybe 3 variable, but output says only one. So that means your function, it would be like that. So that it would be uh, like that. Maybe it give only the values, kind of like this. The whatever the sum, it will only give the real value. This is called scalar valued. Vector valued is, again it is the same. Domain will be contained as is, this is R3. So 3 variable will be in the domain for the domain, saying to be in, it is in domain. And the output is, here you can say it is R cross R. That means one coordinate says this for this R, the second coordinate says for this R. So that means your function maybe look like coordinate wise, like here I just wrote, this is comma here, and so this is for first coordinate and this is for second coordinate. So such kind of function is called is a vector valued function.
Excuse me, sir. Sorry for interrupting, but for scalar valued function, no matter what the domain is, it could be R3, could be more of, could be R4,
It
R5.
could be R3.
It could be R. Let me in generalize. Let me write in generalized form. It is Rn to R. R is a finite natural number, if you want to say finite natural number, and this is in more, saying to be in more general form. And for vector value, if you write, this is Rn to Rm, where n and m are any finite natural number, you can say.
So,
So
R3 to R3 also we can get.
yeah.
so this is one kind of this is saying to be giving a value. So this is
Okay.
vector value. Hello.
Excuse me, sir. Yeah, I just wanted to ask one thing. For scalar values, no matter what the value of n is, the output will always be in R,
R.
in single linear form.
Yes.
And for a vector valued function, there would be another. There will be converted to another scale. Like for Rn, it could be Rm, any values.
Any value in Rm means it will be in a coordinate wise. You can say here is only one coordinate, only R is here, but you can say for the vector valued, for example, here is 2 coordinates. Similarly, if it is in R3, it will contain 3 coordinates.
Okay, sir.
If it is output is R4, in R4, it will contain 4 coordinates, and each coordinate contains some function. means saying to be this is one function, this is another function, this is another function. So each coordinate will be a kind of function.
Or sir, does the value of m depend on the value of n,
No, no,
or
no.
it could be
No, no,
anything?
no. It could be anything. It is more
It-
general.
Okay, so it is equal to greater than and less.
No,
Both
no.
the
There is no relation. It could be like this also from R to R3. So you can
okay,
see
okay.
that only this is, but this is codomain is the function. For example, for this kind of function is fx is equal to x square comma x cube. For example, I am saying x square plus 1. You can see that this is in 3 coordinate game, and see you can see that each coordinate gives a function. It is all are different functions. In more generalized form, if I will write, so it will be look like this: f of x y. Let's say this is, or maybe in this xi kind of, let me write x1 x2 xn. So it will be look like this: f of f, let me f of f1 x1 to xn comma f2 x1 to xn comma this is till the m times, this is m times, so f of x1 to xn. So these are m coordinates. So each coordinate will we have like a function, as here you can see, or maybe here also you can see. Each coordinate is we have like a function in the same number of variables. May not also only one. It contain only one variable also. Like it will be like a function. Okay. So this is a vector valued function. Now the next lecture is content part.
One question, please. Sorry.
Yes,
Can
yes,
R2 to R2 be also called as vector valued function?
yes, yes.
2 to
Yes.
2 also. Okay.
This is more generalized form. I just told m and n can take any value. It can be both same, both are independent. Means independent. You can give independent natural number to m and n. It can be both same. It can be see that it is 1 here, it is 3 here, or maybe it is 3, it is 1 here. So you can say one is one kind of vector valued function, but we just name it like it. See that this is R3 to R1. See it is called vector valued function. So sorry, it is a scalar valued function. I just naming it. So if you are more safely, you will say, let's assume m is greater than m, if you will say. So otherwise you will say it is a scalar.
Okay. Okay.
So no need to be confused. Still it is, you can say scalar valued is one kind of vector valued, but we name it as a specifically scalar valued function. So let's put in the here condition that yeah, maybe m is greater than 1, just that's all. So because I am just for a special case, we are calling it as scalar valued.
Okay. Thank
Sir,
you.
in
Thank
vector value function, m is greater than 1 always.
So this is vector valued and this is a scalar valued function.
Sir, in a scalar value function, m is always equal to 1.
Here is m for scalar valued, m is always equal to 1. Right side, or maybe this codomain will be always a real number. Okay, so this is all about for vector and scalar. That's all in this lecture. And so this kind of function, vector valued function kind of function, no need to worry. This kind of function, if you just study this kind of scalar valued function, that's all for study to enough this one. So that's why in this, or maybe in the studying this multivariate function more, uh, we are concentrated, or maybe concentrated on studying on this kind of scalar value function. This is when you study this thing, this implies a very like easily, like we having like saying to be this function is continuous means just say each coordinate is continuous. Saying to be this limit of this function is exists, so saying to be each coordinate have limit exists. So what it means that each coordinate is one kind of scalar valued function. You can see that because of this reason is enough to study scalar valued function. You can see that each coordinate is one kind of scalar valued function. So if you say this vector valued function is limit is continuous, so each coordinate have whatever the scalar value it contains, it should have limit, continuity, differentiability, what have. If any one of them is missing, like this coordinate is missing, saying to be limit is not exist, so this vector valued is, you will just say that this vector value's limit at that point is not exist. If any one of them is missing that property, the whole function, vector valued function, will say, you will say that that property is missing, that function vector value. So that's why studying this scalar valued is just enough. This kind of function multivariable is just enough to study scalar valued function. So this is the differences, and this is, that's why we more
Sir, for scalar value function, the n equal is greater than 1, right, sir?
scalar value function. Sorry.
Sir. Yes, sir. Yes, sir. Scalar value function, the n will be always greater than 1.
M is n is always greater than 1. Okay, so still you are okay. So okay, so okay, if you are putting condition, yeah, let's put here maybe more. M also greater than 1 for scalar. For scalar, for this is for vector. This is for vector, and this is for scalar. Let's make it here is n is greater than 1. Then it will be good. Otherwise, still see, one variable function is also, you can say, scalar valued function. This is one variable function, but still it's behaving like, okay, because you are getting scalar means you are getting output as a real number. So for this also you are getting output as a real number. So for one variable function you are getting output as a real number. So still it will say it is an scalar value.
Okay, sir. Okay, sir.
So I want to make it here condition. So don't worry with this kind of, just I am just saying what is differences in scalar and vector. It will properly, if somebody is asked question, it will say, he will surely at least give what is scalar, what is vector, he will mention in that, and maybe also he will be surely write like this. First he will give you to this kind of notation, and then he will define the function. Don't leave it there. Okay, so this is a scalar vector. So next is partial derivative. So partial derivative, as you gone through in math 1, saying to be just, I will not saying math 1, I will just say calculus portion. So if you in one variable, like if you have a function x square plus 3x plus 1, so so derivative of this function is, we used to used to be denoted like f prime, and in more explicit way, if you will write, it will be look like this. And so just derivative means, hope we are not going to discuss mostly as what is the derivative exact, like it is the one kind of x to the power n, derivative of this kind of function is going to be n into n.
Next is to n minus.
Just recall the derivative of, let me clear to you, just recall the derivative of a specific kind of function like trigonometric function, polynomials, or maybe a kind of this function x to the power n. What is the x to the power n, e to the power x, or log. Just recall the derivative of this kind of function. It will be enough to deal with this multivariable. Okay, because this whole thing is depend on this kind of the taking the partial derivative. I will tell you, will means derivate with respect to one variable. Partial derivative means will derivate that function with respect to only one variable. So so one variable means you have to be strong on this single variable. As I mean, single variable means this calculus portion. So derivative of this will be 2x plus 3. That's all. So constant function, derivative of constant function is 0, and this is x to the power n. Derivative of this is n into x to the power minus 1. Derivative of e power x is just e power x. Derivative of log x is on base e, we will say. So it will be just 1 by x, I think. Is it?
1 by x.
So and derivative of sine function is cos. Cos is something, whatever is that, we'll doing the derivative, you'll see that while studying this multivariable. Yes. So partial derivative is so this is saying to be the derivative of or derivative of this single variable function. We got this one. So if you have a function like this in the scalar, just a scalar valued function, let's say this fx is equal to x square plus y square, so it contains two variables. So x y, suppose this is one kind of function of multivariable. This is scalar valued function. The partial derivative means you will derivate, like here you are derivating with respect to x. So partial derivative means the whole word. If I will somebody is asked also, it will say partial derivative with respect to x or partial derivative with respect to y. So if somebody is asked question, so it will be, you will ask like this: partial derivative with respect to x and partial derivative with respect to y. So let me tell the here what it means. So it means that f prime x is in limit form. This is just writing in the just writing the formula. If you know these things, just derivate it. Otherwise, in limit form, it will be look like this: limit h tending to 0, f of at a particular point. If in more specifically we write, let's say f prime at a. So limit h tending to 0, f a plus h minus f of a upon h. So in variable form, if you will say, so like f prime x is limit h tending to 0, f of x plus h minus f of x upon h. At a point it look like this, or in the variable kind of, so it will be f of x plus h minus f of x upon h. So this is the mean of derivative of one variable. So same thing. So let me write here exact the same definition. There is no differences also. You have function f of, this is in two variable, x square plus y square plus xy. So saying to be partial derivative, it will be surely written with respect to which variable. So I'm just writing with respect to x variable. So it is used to be denote. It is called, this sign is called del, or somebody is called deba. So I am calling it as a del of x. It is the just what is spoil form of d, you can say, if you'll say it is. So del of f of x y. So can you help me to write this how it will be? I am just doing the partial derivative with respect to x. So can anybody tell what will be like, what, how the definition in limit form it will be look?
You're looking for the limit form or the partial derivative of the function?
Limit form. Just asking for limit form.
It would be limit.
At a point, let me clear with the at point. It will be more clear. So what will be that?
So it would be for if we are going for x, if we suppose that a is the valued function of x, that would be a plus h plus uh, a plus h
Comma b
minus f a comma b
b divided by h.
divided by h.
So you can see that partial derivative means we are getting, this is called rate of change also. We are changing it with respect to only rate of change we are getting only with respect to x coordinate. Here is x coordinate. We are changing, we are getting the rate of change with respect to only x coordinate.
So sir, for this particular partial derivative, we are considering b or y to be constant.
Y to be a constant. So if in the variable form, if we will write, it will be look like this. So limit h tending to 0, f of x plus h y, so minus x y
X comma y divided by h.
So you can see whatever we are increasing or incrementing in the x coordinate, but y is just like whatever we have. We are not changing the value here. You can see just exact y. Only we are incrementing or whatever we are doing only in the x coordinate. You can see that we are incrementing here only the x coordinate a plus h. So this is called rate of change of the function with respect to x, or rate of change of function with respect to y. And this could be written in the video lecture. If you'll see, it will be, sir have actually it should be written a proper way. I just here given the in the more algebraic way. It should be written like this: limit h tending to 0 f of a b, okay, plus h time 1 0 minus f of a b upon h. You can see that whatever you multiplied the vector 1 0, let me make it in the coordinate wise also. This is h, this is y. So x coordinate only this is unit vector in the direction of x axis. So this is 1 0, okay. So this says we are multiplying the unit vector with some real number, where is h, and adding with this exact value, means it is incrementing only in the x coordinate. If you will solve it, if you will see that if you solve this expression, you will exactly get this one. You can see that multiply, and after multiplying you will add coordinate wise multiplication you will do, it will be h and 0, and this is a b, and then after you will add, it will be coordinate wise addition you will do. So exactly the same thing you will get here. So more properly, if you write in the video lecture, if you see, it will, sir, is written like this, and this is called the partial derivative with respect to x. Let me show you the video, maybe more clear to also if you rewatch again. So once you done with maybe this session, maybe if you rewatch again, it will be more clear to you how what is sir is teaching. They see that h, what is partial derivative, sir is more generalized form has written. Sir have told about x1 x2 xn. So and you can see that h and a tilde is actually, don't worry with this tilde sign. This is called, this is like we are in this video, sir is a tilde means here a1 a2 whatever in the if you are taking in rm a tilde from rn, so a1 to an. So that's the meaning to be writing in the this vector as a tilde. This vector means this point a tilde, saying to be a tilde. Okay. So and here you can see that h time ei. Here is, I think sir have given also, ei is actually 0 0 0, ith place 1 and rest all are 0. 1 will be at ith place, as here you can see we have just only 2 coordinates. So that's why I just for the, this is for one variable. So sorry, this is for two variables. So I am taking the partial derivative with respect to the first variable x with respect to x coordinate. So that's why my one is here and rest is 0, which is here 0. So this is, sir have written more generalized form. That's all. There is no difference. So this is called partial derivative with respect to x, and in the partial derivative, now the partial derivative with respect to y, partial derivative with respect to y, if you write, it would be like this. If you notate it, we used to notate like this: del of y of xy, or it would used to be notate like this also, fy, just suffix y also. Here we can notate it also f suffix x also. So and in limit form definition, it would be f of x, sorry, limit h tending to 0. You can see that x would be the y x coordinate would be the same. We are incrementing here y plus h, some small number minus exact value at that point upon it. This is the limit if you will evaluate. So this is called partial derivative. Let's take an example that then it will be more clear to you. So like for example, I'm taking. Am I audible to all of you? And
Yes, sir. Yes, sir. You're audible.
Yes,
Yes,
and
sir.
is it clear? What I'm saying?
Yes, sir. It is
Yes,
clear.
sir.
All of you are
Yes.
getting.
Yes, sir.
Yes, sir. It is
Yes.
clear.
Stop
Clear.
me if you are not getting whatever I am relating also from video. Please stop me if you are not able to relate also. So maybe I will write the whole expression if you are not relate. It is just a more generalized form. I am just telling about in the two variables.
Okay. Okay. Yes, sir. Yes. We are
Sir,
able to
while
relate. Yeah.
you were teaching, I had a doubt. We are derivating the very vectors, but what are we supposed to obtain after that? Why we are actually interested in knowing the change in vectors?
Uh-huh. Okay. So why we are doing this partial derivative,
Yes, sir. Yeah.
or maybe why rate of change with respect to x only or with respect to y only? This is one kind of change saying to be this is called rate of change with respect to o in the with respect to rate of change with respect to y variable or with rate of change with respect to x variable. In the more general case or in the proper word, I think let me say the exact proper word. Rate of change with so why we are doing this all? See, once when you will study like whatever you used to. So let me give an example, then maybe it will be clear to you. So, like in one variable, what is the real life example is, suppose a bike is uh, uh, like bike is speed of a bike is you are able to get with respect to time is like this: x square plus 3t plus 3 t square plus t plus 2. So suppose a bike is running and speed of the bike you are able to get with respect to time. Let's say after, like if you will keep the t is equal to 0 means your bike is still running with the 2 meter per second. T means here second, in second I am saying 2 meter per second. If you give, what will be the speed after of the bike after 5 or after 5 seconds, means you're just giving the value exact, means just incidence after the or exact at time 5 seconds, what will be the speed of the bike. And so just give the value, you will get the speed of the bike meter per second. Okay. So
Yes,
what
sir.
will be the now whatever you are getting speed, see it is a one kind of function, and by speed of the bike is increasing how the when the time is increasing. So what is the rate of change of increase, like what is the rate of change of speed of bike is increasing, like per second how much it is increasing. So you used to take derivative of it, what is means f prime t. So this gives 2t plus 3. So this should be what you are doing here. Here you are doing taking the dt of t. So means you are dividing. This is one kind of, you are dividing. This is also saying to be like this, right? Del you are means incrementing in f, small increment. You are incrementing in whatever increments, and after incrementing in y del t, whatever output you are getting, you are dividing it. So this speed, it is one kind of, you if you studied in physics, this is acceleration called. You studied in acceleration, this is called acceleration. And
Okay, sir. Yeah.
this is kind of, this if you relate, this is meter per second whatever you will get here, because of division, like here is meter per second the speed is, but after dividing the second will be square. So this is a unit of acceleration. So this
Yes,
much,
sir.
like whatever how much you are after time, whatever the time is increasing, you are how much you are increasing the, how much speed is increasing in just a small portion of time. This much each after 1 second, if you just uh, uh, like after 1 second the speed would be saying to be in the word this is called acceleration is itself called like this much acceleration torad in the Hindi. I know that torad, this much torad in your bike is like just
Yes,
a
sir.
second you
Yeah,
are
yeah.
speeding it.
Yes, I got that. Yes, I got
So,
that.
so similarly, if you have a function like, let me in the real life example in two variables. Suppose your uh, you are suppose in real life example.
So we can say, sir, speed and the friction.
High speed and friction also, yeah, that is good also. Like it's depend on like your road is, if you are your bike is running here and slowly your road is going to be more uh, rough, so time is also effect on the speed of bike, and this road also, this friction also effect on your speed of the bike, sure as your road is
Okay.
also slowly up. So this saying to be this is t, and this is, or maybe after time t, this gives your speed, but y variable says it will depend, it will affect your speed of the bike, this friction also. So let's say friction is notating as a y, and time is notating it as a x coordinate. So if somebody is saying to be your bike of this speed of bike is this one, sorry, this is y square. So what is the like, this is this is one kind of function. Let me make it in t and friction f, t and f. So this is t square, and let's say of t. Something is there, whatever I am just notating it as whatever you give the function. Your speed of the bike is depends on time and the friction also. The your rough the road is also very rough as you are going to ahead and ahead. So then what like somebody is asked after 5 seconds what will be your bike speed. So you will just give the value, and suppose at you are said at that point your bike will reach, so somebody said like some, you are able to relate the friction also at that point, the friction will be something. So you are exactly able to give the value, okay, your bike speed is like that. So same as here, you
So,
are just derivating it
yes,
here.
sir. So we can actually take two values at our function would be different, varying according to two values or multiple values. We can partially differentiate and calculate what is the rate of change due to particular property of a function.
I assume this is not this exact f. This is different. Yeah, this I erase it with the yes, yes, because there we have two times. Like we have this f also, this f also. So you assume it is yes. Yeah. So so as after t time, what is your speed or how much acceleration in your bike you are able to get, and when your friction is increasing, how much your speed of the bike is affecting. So like the rate of change with respect to time, rate of change with respect to friction, what is your bike, how much your speed of your bike,
Okay,
your
sir.
bike is getting.
Yes, sir. Yes, sir.
So that's why it's needed like saying to be this is, yeah, that's a, the mathematics is just a language of, you can say, if you are in the computer science, so mathematics is a language of computer science, or in the most proper way, the mathematics is language of physics. Because whenever you will study, used to study in physics, more time you like something, if you are studying physics, just convert those things in mathematics, solve it, and again relate to that particular.
Okay, sir.
So, and specifically that language we are studying in this mathematics. So, like saying to be partial derivative means able to derivate. The definition of partial derivative is given like this. That's all. You will see in the MLF more clearly. You will see in MLF what is the use of it. So why
Okay, sir.
we are trying to get this partial derivative means we needed the total derivative of a function. Like partial derivative is it will not say that your function is fully differentiable with respect to the both variables. So that's why you will partially you are able to differentiate it, and there is a proper sufficient condition. If you follow that, then you will say that your function is totally differentiable. That is called total derivative also. So for studying total derivative, we needed partial derivative. We will see this in
Yes, sir.
Excuse me, sir.
Yes.
Sir, sorry to interrupt between, but like I would like to suggest one thing. In
Mhm.
before the quiz exams, like for example, now we are in the maths 2, but when I was in maths 1, we used to have like revision sessions, like where they would discuss some like very good questions,
Yes.
some very common questions.
Mhm.
But in for maths 2, in for quiz 1, like there were mock tests, but not the sessions that like for example Vicky sir would take and the others are that
Maths two also revision session used to be. There are two revision session on Maths two also on 6
yeah,
and
but then the max mock sessions is only discussed, right? But another set in maths 1, very like common they used to tell very common questions. Will that
it
happen?
depend on you, like how if you have doubt in mock, just make as a mock also. Like okay, revision is just a revision, that okay, the whole
Like
syllabus is going
like
to be like
I don't
this.
have any problem. The revision that happened before quiz 1 was also very good. But the revision system that we are used to in maths 1, they used to give like very good like very common questions.
Common question means like as in mock, or maybe as in quiz, or not quiz exactly, maybe similar kind of quiz
Yeah,
question.
similar kind of questions. Yeah. Anyway, so that only I wanted to suggest.
Okay, 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 Soumyadip. Okay, okay, we will consider it. No issue. We'll consider it.
Answer one more thing, sir. If the question is hard, only general question, not related to this partial derivative. Sir, this mock 2, sorry, mock 2, and sir, the quiz 2. Okay, sir. So if we are focused on the mock 2 only, then sir, approximately how much we are able to secure marks? It is more than 50% or 50%.
I don't know that how I will say this. If you how I will say this, like this is one kind of well-defined set or not. So this is not a well-defined set. Like it's depend on
Like, but
person to
the
person how
in
much
the
you.
quiz 2 part, that happens with every time. No, in the one statistics 1, maths 1, we used to see that from week 5 to 8, there were like more questions than week 1 to 4. That will only happen right in quiz 2.
Hmm.
Like the later weeks are being focused on more.
No, actually, the reason is not saying to be only from week 5 to 6. Reason the concepts usually you will use in like vector space you studied. Like
Hmm.
in the week 6, are you already studying null space? Null space is one kind of subspace or maybe one kind of vector space. So how you will say that the topic is only specific on 5 to 8, or sorry 5, 6, 7, 8, because those not only those concept exact thing of the previous weeks you used to be solved in system of linear equation. You will also have seen also in studying this 5 and 6 used to solve system of linear equation in the different in itself in question. You will solve some part of the using the system of linear equation, and then you will get answer. So like not exactly saying to be okay, this is because those concept is used in in this 5 to 8. In math one, you can see that separate kind of also, like polynomial is studying, in logarithmic is studying,
Hmm.
graph theory is studying. These are the separate also, not matching with the, not depending the whole. So saying to be separate means okay, okay, on focus on only the 5 to 8. But here is the not case. Like you can see also as the syllabus, you can see, or not only syllabus, whatever the topic you are studying, you can see it is totally depend on the previous concept.
Like I'm saying because maths 2 is a bit difficult. Not only for me, I think this is the case for everyone. Like week 7, week 6 is a bit difficult. So yeah.
Okay, yeah, with your suggestion, we'll surely consider it.
Okay.
So
And
one more.
yes, Sutmisa is going to be this, probably take the revision session,
Yeah,
and
Shushmita ma'am will take, yeah.
he used to teach very well.
Yes, sir.
Yeah, you all will, like Shubham, you sir, Shukida ma'am, all of them teach very well. But okay, sir.
Yeah. So let's okay, somebody's
Yes, sir. Sir, yeah. Sir,
Hello.
this, sir, again, sir, from the mock 2. Sir, I mean to say that it is not, I am saying, I am asking, it is not that if we solve the mock and we will get this much. What I mean, that if we practice the mock and related questions, okay, not the same, related questions from the online and all the things what are given in the mock, some related different questions, then are we able to get a decent score or not? That
Yeah,
means,
that's why in starting I said please concern those topic which is on the mock.
okay.
It will be more helpful to in the like a fine question is there, so maybe surely from a fine it will be.
Okay,
So
okay,
whatever the topic is covered, if you concern those topic, it will help you to in the quiz.
okay,
That's the
okay,
purpose also mock, to give an idea. Okay, this is going to be like that.
okay, 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 good. So we will secure decent score if we focus on those topics and revise more and more questions related to those
Yeah.
topics. Okay, okay, thank you, thank you.
Okay, so so let's continue with the topic. So that's all about partial derivatives. Saying to be why the reason is also just I told you why we are studying this. Uh, so partial derivative I just given in two variable. So generally you can see if you will see in activity or practice, you will mostly see in the two variable. If you are worried with the three variable, just quickly I am just writing what is also, or maybe I remain to give an example. So that is more important, giving to be in more variable. So let's solve with an example how I am doing, or how we will solve the question. So suppose you have a function like this, maybe more. Let's take a tough function. It will be more clear because writing to be as a polynomial is easy to be do that. So I'm making like xy upon x square plus y square. Once you have this kind of like x and y both should not zero. Okay, simultaneously. This is the mean. And if it is zero simultaneously, then you can say the function value is zero. So this is a scalar valued function. You can see you are getting output as a scalar, as a real number. Okay. Now let's find the partial derivative with respect to x. With respect to x. So what would be? So see, most of the time, let me tell you the differences also. If you have a function like f of xy is equal to some polynomial. Polynomial means x square y kind of very is smooth, or maybe it will not contain any quotient. So easy functions are there. So in that uh, I will tell, okay, remain to tell that. Okay, so let's find with the definition, then I will tell the exact the portion how we will do. So let's find here for the using the definition itself. So
So this
partial
function,
derivative.
so this function, sorry to disturb, interrupt you, sir.
Hmm.
So this function is R2 to R1 now.
This is R2 to R1.
Okay, okay.
And this is also, if you are worried with the sir many time use the piecewise function. So this is called a piecewise function because your function output you are getting in pieces. So if you are worried with the piecewise, what is the piecewise function? Many times I have used the word. So this kind of function called piecewise function. Whatever the proper
Okay.
English.
So
Yeah.
piecewise means if for zero it is zero, and for not zero it is this. This means na. Okay.
Huh. In one variable, if your function is like this, maybe x square, if x is greater than 0, x square minus 1, x is less than 0, and 0 when x is equal to 0. So this is also one example of piecewise. This is if your function is defined like this, and the domain is in the piece of some like that. So that is called a piecewise function. So
Okay. 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 Yeah.
don't worry with the word piecewise function. Okay, so we have this function. Okay, we want to differentiate with respect to x only. So just definition is del del. This is called del del of x. This is limit h tending to 0. F of x, let's make it as in x variable itself. We want to find, because now this is going to be a function. If somebody is asked del del of x del x of ab. So it will give a real number, but it is now in the variable itself it is, so it will be a function. So f of x plus h y minus f of xy upon h. So how the function is defined here? Here is just substitute here, it is x plus h y upon x square plus, sorry, x plus h whole square plus y square minus xy upon x square plus y square upon h limit h tending to 0. So we have this. So how will we are trying to find a limit? Okay, so it's going to be more tougher. Okay.
We remove the h
Mm,
in denominator.
partial derivative. Oh, okay. Okay.
Then it goes beyond to infinite.
Generally in question you will see find the partial derivative with respect to x at points. There are some point is given, so it make easier to give the exact value and solve this portion. Here is the variable, that's why it's make us difficult to solve this. Maybe let me go with that. What will happen, let's see. H tending to 0, this is okay. Okay, let's solve this, see what will happen. So let's multiply here x square plus y square. Here is going to be y and uh, uh, x plus h minus xy, and this is x plus h whole square plus y square. Okay, and this denominator is uh, going to multiply with this h. So x plus h whole square plus y square, and okay, this is one, and this is also x square plus y square in one. Okay, this is going to be a big expression. Okay, this is x square y plus y cube. Okay, actually what we have to do, we have to erase anyhow. After giving this h limit, we have to make it okay, so it is going to be an expression. If you give a value here, maybe ab, some ab means some 1 to some real number or some point, then it be easy to solve. Otherwise, finding the exact expression partial derivative, so I will, that's why it's needed, like solving this big expression. I will give here what I meant to say, this one. So first let's find at a particular point, then I will tell you the how, like solving this is going to be a more uh, we have to deal with the more expression here. It will take
Sir,
time
you can remove
because we have
a h. You can take common h from
both
numerator.
sides. If you take from numerator, still it will be here to h will come here, so we have to, we will be
Yes,
in
yes,
trouble to
yes.
substitute value. So let's take some point at some point, then maybe I will back to here. So we
Okay, sir.
want to find the partial derivative. Let's find at 1 2 at point 1 2. So it will be written as here. So limit h tending to 0, f of uh, 1 plus h 2 minus f f1 2 upon h. So this is going to be the partial derivative. You can see at point, particular point means you incremented here with respect to x, it is, so incremented h, and y coordinate is same and divided by h, limit h goes to 0. So you have a function is defined xy upon x square plus y square. So this is going to be 2 plus 2h, and let me 1 plus h 2 times upon 1 plus h whole square plus 4 2 square, that is minus, at point the value will be 2 upon 1 plus 4, which is 2 by 5. So this is 2 by 5 upon h. This is limit h tending to 0. So this is now take the LCM and first solve the this expression, this denominator. This is 1 plus h upon 1 plus h square plus 2h plus 4 minus 2 by 5 upon h. So this is going to be still 2 okay, 2 1 plus h. This is 5 here, 5 1 plus 5 plus h square plus 2h minus 2 by 5 upon h. We have here is limit is running, is tending to 0. So now take LCM of it. So this is 10 1 plus h minus 2 times 5 plus h square plus 2h upon h into 5 plus h square plus h. So this is going to be 10 plus 10h minus 10 minus 2h square minus 4h upon h, here 5 plus h square plus 2h. This 10 is going to be cancelled here, and this 4h and this 10h is, will give 6h minus 2h square upon h, 5 plus h square plus 2h.
Sir, in denominator 5 is also.
In denominator 5 is also, where is this?
So 2 upon 5.
Yes, sir. 1 5
5h,
times
5.
5h.
I just okay, I just that's why I just okay, 5 is here. Oh yeah, I just missing
Yes, yes.
5 here, 5h 5h. Now you will take common. So here is limit is running beside this horizontal line. So limit h tending to 0, you will take common h. This is 6 minus 2h upon 5h, 5 plus 5, 5 plus h square plus 2h, 2h. This one. My pad is not, this writing pad is not. So, so this is 2h. Now h can be cancelled out, so you have limit h tending to 0, 6 minus 2h upon 5, and here is inside 5, h square plus 2h. Now you can substitute value as h is equal to 0. So this is going to be 6 upon, and this is 0, this is 0, and this is going to be 25. So partial derivative with respect to x at 0.12 of the function is, okay. So partial derivative with respect to is this one. So yeah, we can solve it here also. This expression, like whatever we did, this bigger kind of and easy to solve because of this number. Otherwise, this expression would be also solved, and h can would be going will be surely cancel out, right? You will, when you multiply this whole expression, this is also, so the, when you take like some terms will be cancel out and h you will take common out, and you will cancel out from numerator and denominator, and you will able to substitute value to there, and you will get a function in the some form of x and y. It will be that. So what would be that exact function? So there is a, sir in the video also told, if you have a function like this, f of x y is equal to, let's say, 3x square plus y square plus say xy. Okay, you have, if you have suppose this function, so partial derivative with respect to x is, just assume y as a constant and derivate each term with respect to x. So it, what would be here, 6x, and this is you second variable, you will assume it as a constant, so this is going to be 0, plus here is again y variable, you will think as a constant, so partial derivative, sorry, this is going to be only 1, so this is going to be by here, so 6x plus 5. So this is the way solving, like if you have a smooth kind of function, means polynomial or simple function, then directly doing like this, we can do the partial derivative, we can get exactly the partial derivative. You can see that this partial derivative is exactly the function in x and y. Still you will get a multivariate function once you derivate with respect to x or with respect to y. So similarly here also we can do, but assuming to be the, we can do the same thing. Like here, let's take this function, okay, but I will tell the reason. You will always, you have to assume, let me explain, while writing we can, I can explain. So you have this function, okay, both x and y simultaneously will not 0, and once 0 it will be 0. So partial derivative with respect to x will wait again, if you will try to get, again you will assume as y as a constant variable, okay. So you will always assume that x and y not 0. Whatever you will do here, the expression, you will always assume x and y are simultaneously, they are not 0, okay. If you somebody is asked partial derivative with respect to x at 0 0, then anyhow you have to use that this definition, because once let's find that, that will let me find that, then it will be more clear to you. Okay, so what will be here, so derivate it with respect to x, so this is in the quotient form. So what will be here, you have to derivate the this numerator and multiply this, first multiply this denominator, and numerator will be here y, because you can see that here you will assume this y as a constant, minus now xy, and this is going to be 2x only. Please stop me if you are not getting it. Now here is x square plus, yes,
whole square.
so you have this function, yeah, partial derivative with respect to xy. Muted. I muted all. Okay, okay, this is so you have this one, x square, okay, whatever you have expression, yeah, you can rearrange the term. So this, the partial derivative, this you got assuming to be x and y are not simultaneously 0 0. Okay, so if suppose somebody is asked find the partial derivative at 2 5, so you just substitute value here, you will get, because you are assuming, you got this expression assuming to be this one, not x and y are not simultaneously 0. But if somebody is asked find the partial derivative with respect to x at 0 0, then you have to go with the expression here. So here is solving the expression will be easy. As you can say, 0 0 is there, f of 0 plus h comma 0 minus value at 0 0 upon h. So this is going to be f of h 0 minus 0 0 upon h. Here is limit is running. Please consider that. So here, if you substitute here in that exact function, here is y portion, y coordinate is 0. So you will get 0 here value, as your function is xy upon x square plus y square. So if you substitute here, y is equal to 0, x is non-zero. So still your function is well defined, and you are able to get output here, but output is 0. And at 0 0 already 0 value is given. Okay, upon h limit is running here. So 0 upon n means you will get output 0. So limit h tending to 0, limit of 0 function. So that is going to be 0. So if you substitute here 0 0, it will be very difficult to you. Like, not difficult, because your function is, you will get 0 by 0 form. It is not going to work here. For non-zero it will work. But for
So
0
can
0, you have to go with this definition, limit definition. Yeah.
so this one can you again explain?
Sorry, Bhavna. This which one?
This 0 0 part.
Here,
0 minus 0.
0 minus 0, your function is xy upon x square plus y square. So your x coordinate is this, y coordinate is 0. So if you substitute here, it could be h times 0 upon h square plus 0, which is going to be 0, right? Because the numerator is 0 and denominator is still upon h square, which is going to be 0. That's why 0 minus 0 you got, and limit of 0 is 0.
Thank you.
So that's why many times where the function is like where, so as you in calculus also, calculus person also, you gone through that, where the break is there, pieces are there, where the function is like this, you have to very careful with that, and you used to be do with the definition only. Here is also will they do the same thing. Where is not break, where is not break, here it says there is no break, and your, for the general case, your function is defined like this. But at 0 0 there is break, and your function is defined like this. So where is break, in that around you have to be very careful with that, and you have to go with the definition as the partial derivative definition has. With that definition you have to go. But apart from that, yeah, you have already the formulas, just derivated that and get the values. So at the breaking point, we have to be very careful with the dealing with that, and do the definition, exact definition of the derivative or partial derivative.
Sir, over here, um, for 0 0, we could not even do it because the function was a little strange. We would get 0 in the denominator. So is
Yes.
that why we had to go through this formula method? Or we would have to do it in all kinds of functions while we are looking at the point 0 0?
So while looking at 0 0, like how your function is defining, if you are dealing with like in numerator at 0 0, you will get 0, so you are in trouble. So mean to say, if you are, suppose you are okay, you are substituting here, okay, what I suppose somebody is asked at 0 0 find the partial derivative, you did this process whatever we have, and okay, you got this expression. Now substitute at 0 0, you will get 0 by 0 or indefinite form. Okay, once you got indefinite form, so what you will write in your answer, so you have to go with the definition. Okay? Otherwise you will not get answer. In the definition, while dealing with the definition, limit is not exist, then you will say the partial derivative at that point is not exist. Dealing with the
Is 0.
Dealing with the at that point, that definition, dealing with the,
So it's because of the nature of the function that the division results in a, the denominator becoming 0. The function itself is in such that if supposing the top function was just simply x plus y, then that would not be the case, would it?
Yeah, then there is no issue, just substitute value at 0 0 also. Yeah, that's why, where is your break, where is you are facing difficulty in the function itself, it is given. So that area you have to be very careful at that point, at least you have to be careful. Suppose your function is defined like this, f of xy is equal to xy x minus 1 whole square plus y minus 1 whole square. See that here is the difficulty. Okay, remain to tell you the domain of the scalar valued and vector valued. That portion is still remain. So here is, you can see that the if you tell the domain here, what you do with the domain here? At each point you are able to get value at any
Yes.
real number, but the problem
Yes.
is at 1 and 1. If you substitute here 1 and 1, in numerator you will get non-zero number,
Zero. Yeah.
but in denominator you will get 0. So if you tell it what is the domain of this function, if somebody gave like this, the domain of this function is going to be R2 minus this one. Just remove that
Okay.
one.
So 1 will have to look at separately.
So suppose now your function is defined like this: fx is equal to f of xy is equal to xy x minus 1 whole square plus y1 minus whole square. So when x and y not equal to 1 simultaneously, and 0 when x and y are 1. At 1 your value is something. So at 1 you have difficulty here, not 0 0 is easily, like if you substitute here 0, your output will be 0. So do the partial derivative with the exact assuming to be as a y constant and x constant, there is no issue, you can deal with that. The problem with this one, so you have to
Is
be
the coordinates at the break point.
at the break point. You have to be careful with, and you have, whenever somebody is asked find the partial derivative at break point, so you probably try to go with the definition. Otherwise, if you substitute in the expression whatever you got while doing the partial derivative, like doing to be y constant, x constant, you will get 0 form. That's why you will go with the definition. Okay. Otherwise, you are able to get value not in indeterminate form, then that would going to be your value.
Okay. Thank
I
you.
have a question here. At 1 actually it goes to infinity, isn't it?
1 is going to be infinity. Sorry.
You put it as x minus 1 and y minus 1. So if it is x minus 1, it is 0. Y minus 1 is also 0. Anything by 0 is not tend to infinity, right?
Not tending. So what it mean by infinitive then? So my question is from you. What is going to be infinitive then? What it mean by infinitive?
Very large number, which is unknown.
Unknown. Large number, we don't know how it is. Maybe I don't know what it is, but infinitive says you don't know the number. That's the problem. So you are getting infinite, means saying to you are, that okay, we have infinity. You said that okay, infinity. But what is this number? I am giving again a separate two function. Okay, it is like this. It is xy upon x square minus 1. Okay, plus okay. It is like this: x square plus y square minus 2. Now, what is going to be its domain?
R without 1
Without 1 okay.
Without 1 minus 1 1 minus 1
minus 1 minus 1 1.
Yes, minus
1
yes.
minus 1.
4.
These points are going to be create problem to you. So once you substitute 1 here, you are saying you will get infinity. Okay, you got infinity. If you substitute minus 1 again you will get infinity. So what is this infinity? You are not exactly able to get exact real number. Infinity is used to say okay, very large number. That is not saying to be a proper word. Infinity means you don't know the value. That's the infinity. That's why we have to deal with whatever we just said about. Okay.
But my question is more related as to why it is that you had written it as 0 over there.
It is 0 by 0 form, not in numerator also 0.
Numerator, why is it 0 if you substitute 1 and 1?
If you substitute here 1 and 1, you will get in numerator, you will get denominator, you will get 0. If you substitute minus 1 and minus 1 also, you will get also again in denominator, you will get 0. So
yes, that is a infinity, sir.
That is again going to be infinity. So what would be then? That's why the what now in the set form, what would be the domain of this function? So this is going to be R2 minus. You have to remove that point. So 1 you have to remove, or whatever here is, you have to remove from this R2, and rest all are any. Is there any point also? 1 0, no. 0 0, no. 0 1, no. So only these points creates problem to get output, means it gives output as a infinity only at these points. So remove those points. So now the domain of this multivariable function is remove these points from R2. So yeah, that's the I meant to say what is going to be also we studied here domain portion.
Hello, sir. In limit, we can only form 0 by 0, infinity by infinity. Then we can use limit. Otherwise, we can't.
So that is in calculus portion you have just studied about this indeterminate form.
Yes,
so
but
in that case,
here comes 1 by 0. That is means infinity. So limit does not exist.
Limit is not exist. No, here is your function is not defined. That's me. Limit is there is I am not using the word limit. Here is just I am asking domain. What is going to be domain? At that point you are unable to get exact real number. That's why that at that point you will say that function is not defined, or those points is not going to mean its domain. In other word, different word in you can say. There is I'm not using the word I'm not using the word limit. Just saying to be what is the domain or where the function is not defined. That's all. Limit is the different case. Now the question is, if you want to find what is the limit means. Limit means
approximate value higher function is not
as you are going to that side, like as you are wondering about at those points, what is your output is going to be in around, where is your output is going, like you are in R2, okay, your point is here 1 2 somewhere. So whenever you are going to this point, okay, around this point, what is, suppose your function is now giving the output here on this real line, okay, your function is assuming to be f. So in the visualized form, if you will see that it will be look like this, okay, your domain is let's say x axis, y axis, and output is somewhere different. It is not in you know that in from R to R function you used to denote like this, okay, like here is output, here is input, output is somewhere, so you are able to only play with the xy axis. But here is not the case. You are the plane is input, xy plane is input, our output is somewhere you are getting, so separate place is there, okay. So whenever you are rounding to this point 1 2 or 2 1, whatever your limit means, whenever you are going to close at this point, your output is where is going to be at around this point or this point. That's the mean of limit. Where is your you are getting at which point you are getting your output, around to this point or this point or this point, where is, whenever you are very close to, or you are wondering around this point, where you are getting output at this point or this. That's the meaning of limit. The same meaning is in the same in first variable also, means in calculus part. So the same meaning is says, same meaning is a limit extending to a, where is your function is getting, means whenever you are, suppose here is 0, whenever you are wondering about this point, okay, where is your output is getting, it is here or infinity, what is your output, where you are wondering, it is it is to be a fixed number, or it is a infinitive, it means unknown. Still if you are wondering around a, you still you are getting unknown number. Or if you are around a fixed number, you are, whenever you are going to close this number, you are getting close to your output is, you are able to get this number. So this number is actually called limit of this, right? This number is called, you are able to get output around this number. So that is called your limit. Here is also, if you are able to for R2 multivariable, you are substituting your limit. So you are getting output as a scalar number. So yeah, okay, you will say limit is this, means somewhere, let's say this is L. So we are getting the limit as L. So that means we are going to close here. We are getting the numbers close to this L number. That's the mean of limit. In sequence term also saying to be the same mean of limit, same meaning of limit. There's no difference. Means whenever you are going to close a number, what is your output? It is going to be a particular close to a particular point, or it is going to infinity, or what's happening. It's still your, it is told by your limit. So limit also clear to you? What mean by the limit? I don't know. It is clear to all of you or not?
Yes, sir.
Okay, so this is all about the partial derivative. The third lecture is that is the limit term scheme, and I just now started
So
with
your
the
voice is
limit
break.
term, limit word. So in that video, yeah, sir,
And here, sir.
Sir, your voice not clear, sir.
It's showing me also if my internet is unstable. Let me check one. Okay, so now I hope it will not break. Clear, right? Not clear still.
It is clear now.
Yes, sir. Yes, sir.
Okay. It's not breaking, right? Is it?
It is
Derivative,
better
that's
now.
all.
We can hear you.
Yeah. So partial derivative is all about this. What we did. Now, if you watch the video, it will be more clear to you. I hope. And sir have solved the example also in 3 variable, also 2 variable also. And each time is, see that if you see this question, rate of change of f with respect to y, means find the partial derivative of this function at this point with respect to y. So see that the sir have solved what is the mean of, right? He wrote just in the h time 0 1 0 kind of thing. Otherwise you can go with the whatever we did, the same expression tool. So this is all about the partial derivative and the geometric approach of it. Partial derivative to see. The limit thing is very important. Oh, here is written remain to the third lecture is directional derivative. Okay, so that is one kind of partial derivative, not partial. Partial derivative is one kind of directional derivative. So let me go with that. Then we will move to the limit thing. See that what we did here, the partial derivative. Okay, we have function f. We have a function. Let's say, and now assuming it is from R3 to R scalar valued function. Okay, so partial derivative. So this function is going to be like this: f of x y z with this sum will be some f of x y z y z. Here will be some expression. Okay, this is f from R3 to R3 to R. So here will be some expression in x y z term. Okay. So partial derivative means partial derivative with respect to x means, as we just said, limit h tending to 0. So in three variable it will look like this: f of x y z plus h time 1 0 0 value at that point upon. This is going to be with respect to x, with respect to y, it would be limit h tending to 0 f of x y z plus h time. Now here what will be 0 1 0, because this says the second coordinate. We are incrementing in the second coordinate h time, not h time plus h, we are increasing h. Some number h is any positive real number or maybe negative real number, we don't know. We just said here is the limit h goes to 0. Okay, now here this one minus value at that point on h. So this is the partial derivative with respect to x, sorry, y, or called rate of change with respect to y. Now see that this is, see, if you see that this vector, this point 1 0 0. Now suppose this is it contains three variable, right, x y and z. So it will be come as till three variable we are able to visualize. So see that this, suppose this is the x y and z coordinates. Okay, now suppose here is somewhere 1 0 0. Okay, so R3 again, you can see that this is a vector space, right, with usual addition and scalar multiplication. This 1 0 0 a vector somewhere on x-axis. This is on 1 0 0 is a vector on x-axis visual in the visualized form. Here is 0 0 0. Okay, so we are derivating this function with respect in this direction, right, in x direction, in x coordinate, sorry, in x axis direction. Similarly here, see, okay, here what we are derivating, we are incrementing here h, we are derivating partial, we are doing partial derivative with respect to y axis, means we are doing this increment or these things with respect to y axis. Here somewhere here, suppose 0 1 0 with respect to y axis. And you know that these are unit vector, you know, unit vector is in orthogonal, we have gone through. Yeah, so so hope you know, all of you know that unit vector means what. So unit vector, this is a vector space R3, and we are doing, here is the unit vector in this tells you this y direction. So this is going to be partial derivative with respect to y. Suppose apart from this your vector is here, so what is going to be the partial derivative with respect to, or not with respect in that direction? See, with respect to x is this called this direction, with respect to y this vector tells you, but what is going to be the derivative in this direction, that is called directional derivative. Partial derivative with respect to x means you are substituting here, multiplying h with this vector. Partial derivative with respect to y means multiplying h with this vector. Okay, partial derivative, no, now here is not partial. Derivative with respect, or derivative, what is going to be the derivative in this direction. So the same definition, suppose this point is here, u1 u2 u3, the same definition you will see, and it is denoted by directional derivative a here f. Okay, and surely the question will be asked, directional derivative of the function in this direction at a particular point, or if you are asking for the general case for just saying directional derivative of the function in this direction is, let's say in this direction u is here this u1 u2 u3. Okay. So the same definition, here is the same definition, you will see the differences of x y z, same thing, plus h time. Now this 0 1 0 says for y with respect to y, but we want in this direction, means this right here the direction. So see that this is going to be unit vector. This is always the somebody's, see, let me tell you again. So if you have a vector here, suppose you are in R3, okay, suppose here is the point 1, 2, 3. Okay, so this thing tells you a direction, right? This tells you a direction, but in this direction, what is going to be unit vector? So unit vector you will divide with the norm, right? What is going to be norm of this vector is just divide with the length of this vector. That's make you to unit. So 1 square plus 2 square plus 3 square. So 1, 1, 2, 3, and this is going to be 1 plus 2 plus 3, whatever the length, sorry, 1 plus 4 plus 9, whatever the length you will get here, divide with that length, it will change into the unit vector. So same thing, if somebody says in this direction, means he surely will give you, he will give you a unit vector. Otherwise, if you not give unit vector, just divide with that norm of that vector, it will be in the unit vector. So whenever you are doing this expression, assuming to be this should be in unit vector. So that's why I'm just making note here, this u is going to be unit vector in that direction. Okay, minus, same time, same thing, add value at that point upon h. The same thing, you can see that same thing is written, only this thing is changed here. This says this vector itself says it is a unit vector in y direction, this y axis direction. So in this direction, if we want, that means this is going to be unit vector in that direction, and see that h time the same direction minus value at that point and just divide it. Then this is called directional derivative of the function in that direction. So if you give at a particular point, so directional derivative at point, this point is going to be the same, limit h tending to 0, where a b c, that point, plus h time that direction u1 u2 u3. Okay, this is minus value at that point a b c upon h. This is the exact definition, this is the limit definition, or saying to be, this is the limit form of definition of saying to be directional derivative. That's all the same. That's the thing, is only in this lecture is covered what is directional derivative. Is it clear to all of you?
Yes,
What?
sir. Here, sir, U1, U2, or U3 is a point on XYZ.
So let me give you the example, maybe it will be clear.
Yes, sir, what is XYZ? XYZ is a coordinate, 3 dimensions.
X, y, z is coordinates point. Here u1, u2, u3 is coordinates. Here these are the coordinates. Like it will be point 1, 2, 3. So u1 is going to be 1, u2 is going to be 2, u3 is going to be 3. Okay.
So can you explain through some 1, 2, 3 example?
So let me give you the example. Suppose you have a function f of xyz, maybe in 3 variable. Let me take that. So you have a function like xy plus 2 set. Suppose a simple function I'm just taking. So question will be, it will be like this. Suppose you have a question is, find the directional derivative of the function this, or maybe in more clear form, find the directional derivative of a function r3 to r such defined like this, or such that the expression will be given at 1, 2, 3 at point, this is a point in direction of if he gave the direction, then he will surely give you to unit vector. So in the direction of, let's say 1, 1, 1, so he will surely give you the unit vector. So he see that I just divided with that length of the vector. So find the directional derivative of the function. This is given such that the function is defined like that at point 1, 2, 3 in direction of this. Okay, so how we will do that? So just say directional derivative means d suffix u of f at point 1, 2, 3. Point is given here. U is your, now u is your going to be 1, 1, 1 upon 3. So here you can change you here 1 1 1 upon 3. Okay, this is your d suffix this vector f at that point means limit h tending to 0 f of 1 2 3. Okay, this vector our at that point which point we want h time that unit vector 1 1 1 upon 3 put 3. Okay, we done with that. And minus value at that point 1 2 3 upon h. Now let's solve this expression. So we have this one. Okay, so this is okay, so limit h tending to 0.
Sir, that's u is the unit bit, right, sir?
This is u is unit vector.
Okay, sir. We have to calculate it by dividing with the norm. That's
If you suppose he is not given, then
okay.
just divide with the norm.
Okay, sir.
It will be your, because in the expression it is in the definition itself it is given in the unit vector, so you have to do. Otherwise, who made this question, he is the like going to be responsibility that he should give you in unit vector. Maybe he forgot, or maybe he just said okay in that direction, because still see it's I just given the example right here, it says the same direction. So if somebody gave this direction means, okay, if you're confused with this 1 2 3, so let me engage with this 1 1 1. Okay, maybe. So if somebody gave this only, so still it gives tells you the same direction. Okay, but we want it unit, so just divide with that length of that or norm of that vector. So it is in unit vector. So who made this question, his responsibility, but still the if he didn't give unit vector, he means to the same thing, he wants the same thing. Now your responsibility to make it unit vector.
Okay, sir.
Now okay, so this is this much. So this is f of 1 plus h upon root 3, 2 plus h upon root 3, 3 plus 1 upon root 3 minus value at that point is going to be f of 1 2 3 is going to be 2 plus 6 8, value at that point upon h. Now substitute the values here. This is the x coordinate, this is y, this is z. So in substitute in this function, it is going to be 1 plus h upon root 3 into 2 plus h upon root 3. Okay, plus 2 times z, 3 plus h upon root 3. Okay, minus 8 upon h. Okay, so if you solve this, it is going to be now need to be multiply here. So this is going to be 2 plus h upon root 3, and now this is 2 into 2 h upon root 3 plus this is h square upon 3 plus 6 plus 2h upon root 3 minus 8. So 8 will be cancelled out when you add this at 6 plus 2. Okay. Upon h is our remain. Here is limit is running. Limit h equals to 0. Now you can see that this 2 is going to be, now if you take see this is cancel, so this makes cancel. Now you can take h as a common. Okay, and this is going to be an 1 upon root 3 plus 2 upon root 3 plus h upon 3 plus 2 upon root 3. Okay,
That is h square upon 3.
H square. So you take one h common, right?
Oh, you already removed the h. Okay.
Okay. So yeah, so this is you will get here. Now cancel out this h and now substitute the limit here. H is, it is going to be 1 upon root 3 plus 2 upon root 3, and this is going to be 0 plus 2 upon root 3. So whatever you will get output, it is going to be your directional derivative at that point in the direction is given. So this is all about whenever somebody is asked directional derivative, you have to do all this process, otherwise it will be difficult to you. In this thing is in lecture 6 makes easier. No need to go with this limit kind of. But there is one condition. What is the condition? That your function should be nice. Nice means if you watch that, let me finish with this lecture also. Okay, the terms read with the gradient word. Okay, so okay, let me tell you that one by one. So whenever somebody is asked to find the directional derivative, you have to go with this limit kind of thing. But there is one thing: if your function, so this is the whole process always you have to do to find the directional derivative. But your function is somewhat nice means here nice means your function is your whenever you take the partial derivative of this function, still what is remain continuity. That's why. Okay, so that thing will cover in the next. Otherwise, and means after studying this limit and continuity. So till this lecture, whenever somebody is asked to find the directional derivative, you have to go through with this limit definition. There is no supplement of it. Supplement will come in the lecture 6, I think, and easily you can get that. That is just a few things that is saying to be the partial derivative is going to be continuous, exist and continuous. Once, so if you know with the continuous word already, you know in the calculus portion. So if you have a function like this, and suppose your function partial derivative of this function, partial derivative with respect to x, with respect to y, and with respect to z, these partial derivatives are going to be exist and continuous. So in that case, there is an easy process. That's the word came gradient. And gradient is nothing but a gradient of a function is denoted like this. This is ulta triangle, or this is called nebula in the English. In the mathematics, this is called nebula. So this is the notation of gradient, and this f. So gradient of x means partial derivative of x. Write the coordinates, partial derivative with respect to y. How many variables are there? Write those. Get the partial derivative with respect to that and write in the coordinate y, like this. So this is going to be this is called the gradient of the function.
Can I ask a question here?
Yes, please.
What is it that we would actually term the previous problem solution as? We have written it as 1 by root 3 plus 2 by root 3 plus again 2 by root 3. What is that? Is in a line normally? If you
no. So this is a real number. Just you add. After add this is going to be a real number.
Correct. It's a real number, but is that the gradient? In a line, we would say a gradient or slope.
No, so this is directional derivative. This is not gradient here. Now I just started with the word gradient after this.
Okay, fine. What do we call that? It is just partial derivative.
Directional derivative. Directional derivative of the function at this point in this direction. We got this directional derivative. Now so this gradient, what is the ahead thing?
What does it represent?
Actually, I am trying to convince you that gradient makes easier to find you to that directional derivative. Gradient will help you to easily find the directional derivative, but there are some conditions on the function itself. What are those conditions? The conditions are partial derivative, how many variable that contains. You will do the partial derivative with respect to that, and that those partial derivative should be continuous. If once that then it makes easier to you can easily evaluate the directional derivative, but the continuity still remain to study for this multivariable. So I just quickly I just saying it makes easier to find the directional derivative, but you will see this later. The whole process we do before knowing to this gradient word, whenever somebody is asked, you have to go with this limit terms, limit expression, and have to find this real number. Means this expression,
Okay.
solve have to solve expression.
Maybe I'll try rephrasing my question so that I can communicate my question properly.
Oh, okay.
Now,
So, okay. Yeah, sure.
okay. In a regular derivative, I mean, like when we are doing differentiation on a regular y is equal to mx plus c or something, m represents the rise and the fall of the rate at which the line rises or falls. Now, when you say directional derivative, how to reinterpret that in a physical sense? Let me ask.
Okay, okay, and geometrically, okay.
Geometrically or any physical sense or anything. Yeah.
So actually, so for example, for there is one good example. In the orientation, I just orientation itself in video itself, I just given the word gradient. So see, so let me tell you again. So maybe better to be the not that example. Maybe I have another example. Suppose you are riding a bike, okay, and there is waterfall. So raining.
Right.
The season is raining, and there are so many. The water is raining, like raining. You are riding a bike, and there is a rain. Okay, the proper word is there is a rain. Okay, and you want to, and also if you will say air also, yes, flow of air also, and you want to make it like you want to move your riding faster, like you are riding a cycle, so you want to make it more faster. So that's the thing. Suppose your function is given something like as previously told you, there is rough kind of thing and time with respect to time and friction. Your speed of the speed function kind of your speed is can be calculated with this expression. Okay, now the thing is I want that direction in which in that like I want a direction so that you can move more faster, like it will less affect this rain, less affect this blow, this air. So how I able to get that direction? So like suppose somebody says please ride in this direction, you will get less this air, this rain and maybe airflow, then you will move in this direction. So what is going to be now the rate of change of your speed, that is the acceleration. Now in moving in this direction, what is your going to be the acceleration, right? So that's the called means that's the needed to be your directional data. You moved your right now. You moved in the direction. What is effect? What is affecting? What is effect on your speed now when you move in direction? What is going to be your acceleration in direction? So acceleration is now going to be your directional derivative of that function in that direction, right? Got it? What I mean to say. I don't know.
Got it.
My English is not that much, but I don't know it's convincing to you to get.
Yeah, I understood. This helps. Thank you. Thank you.
So, sir, there in that
Yeah,
directional one, we got 5√3. So we can say that is the rate of change in the direction
of the
of that
function in that direction.
In
Yeah,
that
of that
111√3 of that particular point.
Yes. Rate of change of the function at that point in that direction.
In the direction of 111√3.
Upon root
3. Okay.
So yeah, actually here is the physical meaning of the why we needed this. So when you will study in week 10, so there is one term came maximum directional derivative, minimum directional derivative. So I just said move in this direction, you will get the somewhat lesser effect of the air and this rain. Maybe somebody's, suppose your mind is like you are able to get that I will move in this direction, then I will get the rain effect, very less rain effect and very less effect of this air. So now what is going to be your rate of change, or now what is going to be your acceleration? So that's the acceleration gives you this directional derivative is actually the acceleration in this direction. If you are moving in this direction, so this gives the acceleration when you are moving in this direction.
So when we moving in the opposite direction, that means accelerate going to minus.
No, it is going to be increase now because of air. You will ride more faster than previous one when you move this direction.
We
So,
here did not apply physics.
so whatever the thing is, like whatever the thing is, like I mean to say what is directional derivative. I just in the physical. No.
Thank you very much. Thank you.
Thank you, sir. Thank you.
So
The next class is going to start
whatever
directly.
in the
Thank you.
physics you want.
Sir, earlier we had done this partial derivative with respect to x and y. So could we look at those answers and check the gradient?
So no, sorry, gradient means no, I didn't get your question.
If I've understood gradient correctly, we're just finding the partial derivatives with respect to different coordinates. First with respect to x, then with respect to y, and with respect to z. So earlier we had done a question where we did it with respect to x as well, and I think with respect to y as well.
Yeah.
So could we use that?
So actually what we are doing, once you find the gradient, so you are able to find the exact at that point what is going to be your gradient. At that point you are able to get value, right? Now take the dot product with the that direction. This is exactly will give the same. That's the
No, sir. What I wanted to know is how the gradient will look like. That
gradient.
The second part is a different thing. So we had, I think, done a question where, if I'm not wrong, where we found for the function with respect to x, the derivative with respect to x also, with respect to y also. I think maybe if we could look at that and find the gradient, and then maybe then it will make sense.
Actually, so I am not taking nine. So this time I'm not going to. We are not going to discuss gradient. It still remain to discuss limit and continuity. I just keep the why I mix up with this gradient word. I just because of this gradient will help you to easily find the directional derivative. That's why I just word uses here gradient. Otherwise, it comes.
We're not doing it today.
We are not going to discuss this today, because it's needed continuity word, and still we are in till the partial derivative. So it still remain to discuss the limit thing. So limit is a big concept, still remain to discuss. Maybe probably I will discuss this today. And continuity is, you know already, what is the continuity? Find if limit is exactly equal to the function value, then the function is continuous. The main theme is remain to this till this time is continuity. I just recall this gradient to, okay, there are some easier way to find the directional derivative, which is word gradient will help you to find. That's why I just recall that. But yeah, probably we are not going to discuss this gradient today. We meant to discuss limit and continuity. So so directional derivative, I just told you physical meaning, and geometrically is visualizing. There is no geometric visualization of, yeah, just physical meaning you got right, but there is no geometric visualization of this directional derivative. Only it is like, yeah, actually only mean to, we will understand with the physical. There is no how I will make it in this form, like in coordinate wise. I don't know. Yeah, actually there is no mean, because it gives a real number. Okay, so yeah, remain to discuss this limit. So in the fourth lecture, I think so, limit is directional derivative done. That's all in this definition itself. This is all about the directional derivative. Now the limit is there. So limit is, sir have told one definition, that is called sequential approach. Okay, so if you are watching lecture, okay, so I will say uh, watch this lecture limit and this lecture also, then do the activity, because continuity is just a limit. Just if limit is exist and function value will the same with the function value, then function is continuous. So after watching this lecture, please watch this lecture, then do the activity here, what is here, because it in both have, sir have covered the limit, how to find the limit. So in this fourth lecture, sir approached with the sequential definition of limit. Let me tell you that exact definition. Maybe it will clear to you what is sir here is saying. I meant to tell you the sequence in this fashion. In this fashion, in sequence in Rn. What do you mean by sequence in Rn, or limit of sequence in Rn? So that is a quick thing that is easily can we do. So see, as you know, sequence. What is sequence? Sequence is nothing but a function. All sequences are nothing but a function, but domain of the function of that function is natural number and codomain is real number. That's all the sequence. The definition of the sequence is, if in this form, in this fashion, if you will write, so domain of any sequence is natural number and codomain is real number. For example, 1 by n, we used to denote it like this. I mean, denote means notate it like in the curly bracket. You will write that expression in the variable is n. Generally used to denote with the variable n. So in the second example, like, and in the set form is we used to denote like this fn, and this is a sequence defined like fn is equal to 1 is n square. So you can, why this n is here? The reason is because of this domain we are notating the variable as n, because domain of any sequence is natural number. For example, another example is, let's say, sequence an or fn. So it will be in the curly bracket such that, or defined like this: an is equal to n square plus 2n plus. Again, n is, the reason is because of its domain. Domain is natural number. So sequence is nothing but, see that these are a function. You are substituting, like what will be a1? You are substitute here 1 plus 2 plus 1. You will get some value. What is the a2? You are substitute here 2 square plus 2 into 2 plus 1. See that n is behaving like a variable. You are substituting. So when we have variable means you are, this is a kind of function. So sequence is nothing but a function, but its domain is fixed. It's a natural number. So that's all about the sequence. And I already told you what is the limit word. Again, if you want to find the limit of a sequence, so here in the function case, we used to find the limit of a function around a point, okay, of a point in the first variable. But limit of a sequence means whenever we see that here is x goes to a, but here is, whenever somebody is asked try to find the limit of sequence means n goes to infinity. When your number is going to be bigger and bigger, what is going to be output of that? The output of that function, the same, this is a function, what is going to be? So in the geometric form, if you'll see, so as your number is increasing, going to, sorry, it is in the real number, natural number. So suppose you are able to notate it here, the numbers are natural numbers, where your number is going to be increase and increase. See, for this sequence your output is 3, for this sequence your output is something 4,
9.
9, okay, somewhere is 9. So for, if as similarly your numbers are going to be bigger and bigger. So So once you're like when you are substituting bigger and bigger number, your number is going to somewhere around a fixed number, or it is going to be still increasing. That's the limit. If it is around a fixed number, that is called limit. This is your limit. If it is not a fixed number, then you will say your sequence is divergent. This is all about the limit. This is that's all the limit of the sequence. That's the meaning of limit. Now if you have a sequence and talk about the limit of a sequence, then the remaining part is now we are going to deal with the limit in R2, R3, how it will be. So same thing as we discussed right now. Once we study scalar valued function, we are done with the vector valued function. There is nothing extra thing in the vector value. The same here. Once we studied, you all of deal with this kind of function. All sequences deal with this kind of sequences. So vector sequence means, let me write that maybe sequence in R2. How it would be? Sequence in R2 means, again I just said, if there is a sequence, its domain is always a natural number. Domain of this sequence is natural number, but codomain is, as just now for in the calculus person you studied, domain is natural number and codomain is real number. But for this course, for this in this week, natural sequence in R2 means domain is still fixed, natural number, but codomain is going to be R2 here. See that these are only the changes. Sequence in R3 is, again it would be a function, but domain is fixed, natural number, but codomain is going to be R3. So what it means that? It means that your output would be coordinate wise. Here your output would be in 3 coordinates, right? That's the mean of R3. That's the mean of R2. Okay. Now here, if you for example, if I will give a sequence, see that 1 by n and 2n. See that? As just now in scalar valued function also we discussed. What we discussed? Each coordinate is going to be a function. So for our sequence case, each coordinate is going to be a sequence. See that? And yeah, but yeah, the domain, see that you will give the values from the natural number. Similarly here in R3, for example, let's see that for example we have, let's say n square comma 2n plus 1 and 1 by n. See that each coordinate is going to be a sequence and it will be in coordinate wise. That's all the sequence in R2, R3. If it is in Rn, if you are writing sequence in Rn means, again the domain is fixed, but codomain is Rn. For example, if you write it like this, then each coordinate is going to be a sequence till this is n times, n coordinates are there. Here, for example, a sequence, let's say this is n square, this is n square, 1 by n square, whatever you have. So n coordinate, each coordinates have contain a sequence. It can be any sequence. So if your whole thing is called a particular sequence in that space means that Rn. This whole sequence is a sequence in this R3. Is a sequence in R3. But each coordinate is we have like a sequence. Similarly for R2. Is it clear to all of you what I just said?
Yes, sir. So if we find the each coordinate limit separately.
So now the term is limit means, that's all. If each term have limit, able to get exact limit as a real number, then you will say your the sequence is convergent. Limit is exists for this sequence. If your sequence is not convergent, any one of them is not convergent, or you are unable to get the limit, then your sequence in this space, in this Rn, is not exists, not convergent. That's all. That's
Sir,
all
could you
about
repeat that? Sir, could you repeat the last part about this limit?
Limit. So if any one of the coordinate is not convergent, any one of the sequence in any one of the sequence in any one of the coordinate is not convergent, means not limit is not exist. So in that case, your sequence, this sequence in this space we are talking about, in this space, is not convergent. If it is convergent, the whole each coordinate contains sequence, it should have a limit. So let me give an example. Let's you have a sequence n, natural number to R2, or maybe in R3. Let me make it in R3, and it is defined like an is equal to 1 by n, 2n, 1 by n cube. So somebody is asked, is this sequence is convergent? So let's calculate 1 by 1 limit of each coordinate. Calculate limit of this sequence is 0. Limit of this sequence is 0. But what is the limit of this sequence? Not exist, because this is 2n. As you are going to be substitute here bigger and bigger number, this is going to be more bigger number. It is not going to be a fixed number. It is still increasing as you are substituting the values. So that means your sequence is not convergent. For example, another example, let's say your sequence is 1 plus 1 by n, 1 minus 1 by n square plus 2n, and let's say n minus 1, n square minus 1. Suppose you have this sequence. So what is going to be, somebody say, is this sequence is convergent? What is the limit of this sequence? This sequence is in R3. Yeah, this sequence is in R3. So this is natural number to R. Okay. So what is going to be limit of it? Or it is first, is it convergent? So okay, let's check that each coordinate. So limit of this sequence is
1.
Okay. What is the limit of this sequence is? This is again 1. It is going to be 1, because this portion is going to be 0. In going to 0, it's tending to 0. So it is going tending, the whole sequence is tending to 1. Now what about this limit? This is n minus 1 upon n square minus 1.
N minus 1 and n plus 1. 1 upon n plus 1.
Yeah, this is going to be n plus 1. Again, it is, where is it is converging? 0.
Yes, sir.
Is going to be. So limit of this sequence. So actually, this sequence is convergent, and limit of this sequence is exactly whatever you are getting the limit of it. That's all.
The last limit is going to be 1, na? 1
which
upon
one?
n plus 1.
This one.
No, sir. Last one.
This is going to be
1.
Why this is going to be 1? We have this sequence n minus 1 upon n square minus 1. So this is n minus 1 upon n minus 1, n plus 1. So this is going to be cancelled. We have 1 upon n minus 1. Sorry, n plus 1.
N plus 1.
So what about, so what is the limit of this sequence?
1, sir.
It is totally like 1 by n. Where is this? Where is goes? It goes to 0. Only just one term added in that. Right?
Yes, sir. Yes, sir. Going to 0. Yes, sir.
So going to be, because as you going to be bigger number, it is going to be big number, and once you divided it, is going to be very close to 0.
Yes, sir.
So many times, if you are not able to get, so assume it like what I am saying. Substitute a bigger number. What is going to be your output? Like that, if you think, maybe it will help to find the limit. Doing with the numeric is okay, but maybe sometime is discussing with the like this. Maybe we get here. I'm substituting a big number. What is going to be then? Like that, we can think also. So this is all about the sequence. That's all in this sequence in Rn, R2, R3. What do you have? And talking about the limit of it. Means that's all studying about the limit, simple limit. Sorry, simple sequence. If you study with the simple sequence, that is sequence whatever you studied in calculus. That's all about for the any space. So once you have this, so now the term comes here. This is all about here, the same things that I've taught. Sequence in RP is called convergent if it is converged to the some limit. Okay, this is, you can see that how it is going to be when it is convergent or not convergent. There are more examples have solved. Now two things have discussed here. Limit of a function. So here is one definition, limit of a function, this one, and one definition is in the lecture 5. Let me show you again, and let me I will tell you the definition also. That's all for then it will be for today till that. So and this is going to be another definition which contain the word curve C. So let me tell you one by one. Because it is somewhat complicated. This is called a sequential approach of limit. There are many ways to get the limit. Sir taught with the sequential approach. He also taught with the normal also, but in the lecture, this lecture 5, in last of the lecture of that lecture. So what is the sequential approach means? In one variable, let's study, it will very simple to in the multivariate also. So suppose you have a function, okay, from R to R, okay, and it is defined like f of x is equal to, let's say, x square upon x square plus 1. Okay, maybe here is x only. So this is the function we have, and maybe minus here. Let's make it minus here. Okay, so we want to find let's make it plus here. Okay, what we want to find the limit, or maybe what is going to be a limit x as x goes to 1 plus 1 upon x square minus 1. So as you simple ways, you know that you will rearrange the term or maybe solve the expression here. It is going to be x plus 1. So still it will not. So suppose this is minus here, then our limit will exist. So as it here minus, here minus. Okay, so now we will cancel it out here, and 1 upon x plus 1 limit x goes to 1, and now we will substitute here the value, which is 2 1 by 2. This is the one way, as you know, in the calculus course. Now there is slightly change in the definition. I am saying, suppose we have a sequence an, okay, a sequence, we have a sequence an. Now this sequence is converges to A. Okay, so now the limit in this function, in other words, say limit of this function at A, limit of this function at A exists if here is, suppose not only a sequence, all sequence. Suppose we have or maybe let me not a sequence. Let me erase it. So we limit of this function exists at 1 or not. The question is when, if we consider a sequence like this converges to f of a or maybe f1. Here is f1. Converges to some number, converges to f of a. So what is the difference? What I'm saying here, let me make it more. Just 1 minute. Sequence we converges to a, what f of a and converts to f1. The definition exact. Say exactly equal to the limit if there is a real number L such that, okay, for all, okay, we are talking about the limit only, not for continuity. You can say in such that a n goes to a, then we say that limit of at a till this and it is equal to 1. Okay. Okay. Just 1 minute. It is converging to 1. Something missing. So there is a real number L such that f of a n goes to L. For all sequence a n such that a n goes to a, then we say the limit of a, yeah. Okay, yeah, okay. So so we want to talk about is limit exist at 1 or not. Okay, for this function we have a question. We want to talk about, am I audible first to all
Yes,
of you?
Yes, sir.
So suppose we have a function and the question is limit exist at 1. So we just evaluated this one. I got okay, we have limit. We for the, let's forget about, we want to check it here with the sequence criteria. So what is the sequence criteria is, if saying to be limit is exist at one of this function, if, what you mean to say, we will say limit of this function L, sorry, limit of this function exist and L, okay, as x goes to 1. This is the same thing as x goes to 1. Limit is going to be L if what is that, if f of an is a sequence. So for all sequence, okay, I'm missing, I'm not for all, this is see, this is going to be a sequence, right? This is going to be a sequence, f of a and b a sequence. This sequence is going to, if this sequence is going to f of a, okay, okay, let me tell you with the example first, otherwise this term will, you will not understand. Okay, so we have a function, this one, f of x is equal to x square x minus 1 and x square minus 1. So I am giving a sequence, let's say an is equal to 1 by n. So what is going to be f of an? It is going to be 1. See, f of an is also will be a sequence now. How it is? 1 by n minus 1 upon 1 by n square minus 1. See that this in this expression only n is there. That means this is a sequence. This is 1 minus n upon this is if you rearrange, if you solve this expression, you will get here 1 minus 1 by n square. So see that this is a sequence, right? When we substitute here as f of an, see that this is a sequence. This term we got. So the same here is here. Now let me read it again. A function f of x said to be limit is exist, or maybe as x goes to a point A. For the general case, and let me make it here. As x goes to A, we say limit exists of a function fx, and which is L if f of a. And now see that f of a is now, as you can see, it is going to be a sequence where f of an goes to f of a. F of an goes where let me with the third terms goes to L for all L. Okay, f of L goes not f of a, sorry, f of this sequence. Now this is a sequence. This sequence goes to a limit L for all sequence, for all possible for all sequence an, which is goes to a here. See, this a is exact a here. I will write with this example. For all sequence which is goes to a. Okay, now next is, then we say that limit of the function exists. Let's back to with our example. F of x is equal to, our case is x minus upon x square minus 1 we have. Okay, we will say we want to check is limit exist at as x goes to 1. So in sequential criteria you will say that as x goes to 1, okay, f of x goes to a limit L if f of an goes to L for all sequence an which goes to 1. Which goes to 1. 1 means, now let's back to our the sequence sum. Now let's solve this, what I mean to say. See, we checked it for the our case. Now let's say an is equal to 1 by n. Okay, so what we got, f of an, we got n upon 1 minus n upon 1 minus n. Let's assume an is equal to n square. So what is f of an? F(n) will be a sequence. What is that? N square minus 1 upon n to the power 4 minus 1. This is another sequence. Similarly, whatever the possible sequence is there in R2, sorry, in R, whatever you have sequence, see that this is the word here for all. For all sequence, whatever you have sequence, whatever you are corresponding output sequence f of n getting, this is going to be L. Then we will say this sequence, this function has limit L, or this thing to be a limit of the function is L. And all sequences, whatever we are possible sequences we are taking, it should go to 1. See, we didn't take here, this is going to be 0. We have to take a sequence which is goes to 1. So let me erase it with the sequence 1 minus 1 by n. 1 minus 1 by n square. So see, we are taking those sequences. We are taking those sequences. See that its limit is goes to 1. Its limit is goes to 1. See that we are taking all sequences which whose limit is going to be 1 here. Now take the corresponding f of an. What is that? F of an is now, let's erase it. Our an is now 1 by n. So 1 minus 1 by n minus 1 upon 1 minus 1 by n whole square minus 1. This is our going to be f of n, because our function is this one. Just substitute 1 by an means here just substituting we are 1 minus 1 by n in place of x. Here is now what is going to be your f of n for this case. Not this is not going to be your f of n. This is going to be your, just substitute in place of x 1 minus 1 by n square. So this is 1 minus 1 by n square minus 1 upon 1 minus 1 by n square minus 1. So see that we are collecting those all whatever the sequence you have, whatever the possible sequence you can collect whose limit is going to be 1. So whatever you have, so whatever the corresponding limit you are getting, all will, whenever this going to be exact L, then we will say limit of the function as x goes to a to the L. Then we will say limit is axis. So let's calculate. We have this sequence, okay? For this sequence, this is goes to 1. So what is going to be limit of this sequence? This is going to be, let's rearrange, let's solve this. Then it will be, this is going to be minus going to be cancelled. Okay, now we will evaluate the limit. It is going to be 0 here. This is 0. Oh, still ring to, this is minus 1 by n square. Okay, now solve this. We have to 1 by 1 minus 1 by n. So this is 1. This is 1 plus 1 by square minus 2 by n minus 1. Minus 1 is going to be cancelled here. We got minus 1 upon in numerator, and we in denominator we got 1 by n square minus 2 by n. Take minus 1 by n as a common. So minus 1 by n in numerator, minus 1 by 1 by 1. Let's take from denominator, take common. It is going to be 1 by n minus 2, right? So now cancel it in numerator and denominator. So you have 1 upon 1 by minus 2. This is going to be minus here. Now limit of it, this sequence is minus 1. Okay, limit of this term only. This is going to be 0. This is going to be minus 2. Now cancel it minus. See that you got 1 by 2. So, and we have just calculated inside this bracket 1 by 2 also. It gave the same limit. I don't know, all of you are getting, I'm just talking about, or I don't know.
Yes, we're getting. So if we get in for the second one also 1 by 2, then we'll say that.
So it is the, see, we just calculated for the our case 1 by 2. Yeah, we got that limit is exist. So whatever you have possible sequences whose limit is going to be 1, the corresponding output sequence will surely give that limit 1 by 2. Then you will say this function is limit exists at that point. Clear what I mean to say?
Yes.
So this is the definition. This is the word is term is written. See that if there exists a real number L such that f of a n goes to a L for all sequences, I also worded here for all sequences whose limit is going to a tilde. Here our a tilde is 1, just 1. We are studying for this time we are studying for calculus only, simple single variable. So our a is here 1. So all sequences whose goes to a, okay, if such thing is happening above thing, then we will say limit is axis for all sequences. So we have to check that. So it is not always possible. How I can say? So this criteria is actually used to neglect that limit is not exist many times. Because how you will collect all sequence whose limit is going to be 1 and giving to be output is exact here. It is very difficult. That's why this approach is to do that. But the sequential definition is this definition is given. This definition. This is the mean of, this is the color sequential definition. And that's the in this this definition sir is telling. So sir is telling for general scalar valued function. Sorry, scalar valued function. So let me connect with it, connect with that scalar valued. But I hope all of you are getting right what I'm saying here. What is the mean and what is happening here?
And in this, even the second one is giving 1 by 2.
Second one also will give you 1 by 2 because already we have calculated, because we have already checked that limit is exist. So suppose if you have now the one thing, suppose if you have a sequence, let's say bn whose limit is 1, okay, but okay, whose limit is 1, but when you substitute in this sequence it is not giving 1 by 2, suppose I'm saying.
Yeah.
Then in that case you will say function limit of the function at that point is not exist. That's all.
At that particular point.
At that point, that particular point, whatever you have, at least you got a sequence. If there is any sequence whose goes to 1 at that point, whatever you want to find the limit at that point, but the corresponding of n is not giving the exact, like different. Suppose you get cn who's going to be 1 and f of cn is giving different also. That means you are taking a sequence whose inside it is working as in domain you are approaching to the same thing, but output is giving different. That's the meaning says to be limit is not exist. It is not giving the different output, it is giving
How do
output.
we find out that if there is a particular sequence? I mean, it's not possible to look at all sequences.
So actually this is not always easy. See, this theory is actually used to prove the theory kind of, I mean theorem. In theorem usually used to prove. In the real life, like in real life means in the general question, it is not easy to exact find the, but in many times whenever you used to prove a theorem, it is very useful to proving that theorem. So this approach is many times uses in proving the theorem mostly. Okay, for example, let me give an example to you. Suppose sine, suppose we have the sequence sine 1 by n. Okay, we have this sequence. So what about the limit of this sequence is exist?
Yes.
Yes. What is the limit of this sequence?
Sine of 0.
Sine of 0.
No, okay, sorry. No.
No, limit of this sequence is not exist, right? Because when you're substituting bigger number, it will give some. Okay, just let me check one minute.
Yeah, it's wave function.
Sine of the sequence 1 by n. What is limit of this sequence? Sine, okay. Let me check. Let me. Of this sequence. Okay, let's say bigger number. This sequence is going to be 0 when sine is, as we are very close to 0, give to 0. Missing something. Simple sequence. I don't have limit. I can. Okay, just 1 minute. This is okay. This is mod of sine n. This is let me check once. This is mod of sine n. N is going to be 1 is greater than here is 1 by n less than. Actually, limit of this sequence is 0. We have a sequence say n is equal to sine 1 by n. Limit of sine n is not exist, but limit of sine 1 by n is 0.
Yeah.
Actually, reason is as you're substituting bigger number, this inside is going to be closer
Becomes
and
0.
closer, and sine is as in close to 0. Sine is also comes to 0.
0.
So yeah, this is what I proved here, this is actually used to prove the limit is exist or not.
So that's one how to prove that I could not understand.
Yeah, so in this course we are not
Fine.
dealing with this is called epsilon. We are not dealing with this such kind of thing. So that's why this is called epsilon. Epsilon is a real number which is greater than 0. That is like used to prove. This is not trick to evaluate the limit. This is used to prove we are exact real number. Whatever we got limit, this limit is exactly true or not. So this is the process to prove. We'll see that when you do the mathematics. But in this course, there is these are not uses. There is no use of it. General thing is just substitute and get the value. So actually, it have. I just confused a little bit that it have limit or not. That's why just checking that. So yeah, actually, as the simple thing is, as you substituting bigger number, you are getting a very close to 0, which science keeps the close to 0 will give to close to 0. That's all. This is the only thing. I just confirming it. So yeah, I was there now. What I was discussing, I forgot to. Okay. What is that? Sine. We are sine. I was trying to tell you where is the function is limit is sine x when x goes to function f of x is equal to sine 1 by x. Sine 1 by x. So is limit exist as x goes to 0 for this function. So to check that this limit is exist or not for this function, there are two ways. Like you have to assume two sequences. Not 1 by x. In other function, mod of simple thing is simply take mod and limit is also mod for mod is also equal minus 1 to the power x as limit as x goes to 2. What is going to be limit of it? Simple function. I am not getting this. Actually, what I meant to say for this question, I am not getting a simple function. Means if you have different sequences and it gives the corresponding output is different, then you will say that limit of that function is not exist. So I just make it. I don't know. I just make it tougher. Means I myself make tougher. So no need to worry with that. I am not this time getting an simple example. Actually, there is one example used to be not exact. You can create also example which have give the output as different as you change the sequence. Means when you change the sequence, yeah, whatever at particular we are trying to find the limit, that is correct. But output we are going to get different. In that case, you will say limit of that function is not exist at that point. That's the mean I want to say. That's all. So that's all for today. I think so. Let's stop now. Maybe next session I only take maybe. So maybe I will continue with the limit and next week continuity and last lecture. 3 lectures remain to discuss that. Only 2 lectures. Limit is still remain to discuss. So
Thank you, sir.
Let's stop the session maybe. Yeah, it's approx 2 hours 49. And in next maybe probably I will take, and in the next session we'll discuss with the limit term. Maybe at that time I will probably take the exact function. This time I'm not getting the proper function. Okay. Thank you so much. I don't know all of you got or not. Whatever. Okay, let me clear to you. Whatever we discuss, is it clear to all of you till here?
Yes, sir.
Only the
Too much.
this
Yes,
portion is I
through
didn't give
lecture
an
we could
example.
not understand what professor said, but it is now Clear
Now
and
clear?
yes,
What
sir.
it mean? What is that video sir is taking?
yes, sir.
Yes, sir.
Okay, so this is all about. We'll continue with the next session, limit, and then continuity, and then gradient. These three topics is there. And your next session is on not tomorrow. It is going to be probably Sunday. All of you got in for this right now.
So it is Sunday. It is on Sunday.
Please check with that. Maybe it is on going to be. Today is 1. This is July 2. 2. Yeah, this is now 3. See that. That's 2. It is on going to be Sunday. Okay, so 2 to 4, the same timing as in Saturday. Slightly change in this particular this session as well. Okay, otherwise usual timing will be. Which is in calendar, update it in your calendar itself. And I think announcement also went to all of you. Okay, please check that announcement also. And otherwise already so view here also. It's going to be on this 3, not 2. Clear?
Yeah. Thank
Thank
you
you so
so
much. Yeah, thank you so much.
Thank you so much.
Thank you, sir. Thank you.
Good night to all of you. Bye.
Good night, sir.
Good night, sir.
Goodness.